So now we've heard about impact analysis, cost analysis, and we've spoken about monopolies and that sometimes tasks are better done specialized by research communities themselves and within academia. Other times it's a more trivial product that is better handled by the industry. So I put to you the question, what about hosting of supercomputing? Is that still something that is rocket science, very specialized and should be dealt with by academia for special purpose? Or does it to some extent have a more straightforward production-oriented element, which indeed can be handled by industry along the same lines as possibly electricity or networking, cables and so forth? This is not a straightforward question. It's very complicated. So I now give the floor to you, our host of this Nordic HPC system, which I'm sure you all heard about. Originally it was Tor Data Center. They have now become Advania, and Kolbjørn here is representing them and will explain to you the rationale of hosting done by the industry, also possibly covering academia. Thank you.
Thank you. Should I use that one?
I think you better. Yeah.
Okay. Hello. Good afternoon. Great to be here with you guys today. I think since you don't know me very well or my company, I think it's sort of it's in order that I do a bit of an introduction. Here is my official title. I'm the manager of business development for Advania, which is a Nordic IT company. And I'm sort of wearing two hats here today. I'm also the chairman of the Icelandic DCI, or the Data Center Industry Group within the Icelandic Federation of Industry. This is a recent group which consists of the two major data centers and some other stakeholders in that industry in Iceland. So without further ado, let's see if this works. Yeah. So the company Advania is actually tracing its roots back to 1939. There was a company called EJS, which started servicing the needs of local business. And as you can imagine, that was typewriters and shotguns, mostly. Of course, a lot has changed since then. Actually, in the meantime there, in the 50s, there was the foundation of a company called SKIR, Skýrslufélag ríkisins og Reykjavíkurborgar, an extremely easy to pronounce company name. And this was a company formed by the state of Iceland and the city of Reykjavik to take care of the IT needs, and similar companies have been formed around the Nordics, I believe, around that time. This is punch cards and whatnot. So today, it's a different story, of course. We're mostly in IT, and this sort of explains the journey we've been on over the last couple of years. We've merged 9 Nordic IT companies into this company called Advania, and we consider the Nordics as a whole to be our home market, including Denmark and Finland, even if we don't have offices there. So today we have 18 offices all over the Nordics, and that's our home turf. We have around 1,100 employees, a little over, and they're distributed so. We have about 600 people in Iceland doing basically IT from A to Z. That sort of comes to the turf. Being in a small market, you have to be able to do more than one thing. It's not the case in Iceland that companies are highly specialized in some one arena of IT and then they jointly solve problems together. It's more like all of this has been sort of the major needs, for instance, running the IT systems for the government, running the Oracle e-business suite for the government, even writing the localization for that has been handled by my company. In Norway, we have 200 people in Dynamics Axapta, which is an ERP software, which I'm not sure any of you are familiar with working with in academia. And in Sweden, we have a company very similar, I guess, to what we do in Iceland. They specialize in what they call agile sourcing. That's a new buzzword. So they, in essence, become the IT department for the business that they are serving. They work with a lot of sort of medium-sized companies in Sweden, municipalities, and they even handle the backend for the Swedish parliament. And we have a small company in Latvia, which is related to our company in Norway. Yeah, this is the mergers, skip that. And this is sort of how we try to focus ourselves. Where we bear down is sort of these 5 key competences, and you can see that in number 2 there's hosting, and that includes our data center business. And the verticals you see there are the predominant verticals you will find in our business, and where we aim to be best of breed, so to speak, and that includes government and education. So HPC, that's sort of why I was asked to do this talk. In terms of to host or not to host, that is the question, isn't it? To either do it yourself or talk to someone like us to come up with the facilities and help you get this done. You have to consider, of course, some of these variables. For instance, and this is my favorite actually, the power price and availability. In Iceland, we have a unique situation in terms of our power production, I believe, and that is on the one hand that it's completely green, so to speak. The only coal we use in Iceland we use for barbecuing, and it gives very little emissions. There are some emissions actually from the geothermal stuff, but they are very limited, and some people, for instance in Italy, I know they don't count them because they would probably happen anyway. That's one way of dealing with it, but those are very minuscule compared to burning fossil fuels. And of course emissions, and this is something that I've sort of, it's a pet topic of mine. The European Union, for instance, has set very ambitious goals for cutting emissions. And the climate science says that if we're going to get away with only a 2-degree increase in worldwide temperatures, we have to do a great deal of things now and in the immediate future. Now, IT sort of gets a get-out-of-jail-free card, because the studies, they say that even if IT is about 2%, or going to be about 2% of the total emissions, it will account for about 15% of the reductions. So people are pleased with IT, but that sort of still leaves a little room for thought. I mean, how are you going to do this? How are you going to power this? If it's just a question of putting a huge data center next to a coal plant or something like that, that's a different scenario. We can't have the invention of cold fusion as a precursor to this. So the other thing is, of course, connectivity and the operational environment. Now, the benefits of outsourcing, from where I'm standing anyway, is number one, you get much better economies of scale. If I have a huge data center and I'm in a situation like I am, and I can negotiate extremely low power prices for the long term, say guaranteeing myself a 3% inflation rate in power prices over the next decade. That's not something a university or a consortium of universities might be able to do in a market like Europe. Same goes for other things, stuff you need to build the data center, and the way you scale it up. If you have a modular data center, you can calculate these costs per increments. If you have a huge data center you build all in one go, you can try to maximize your economies there. And also, I think we're at the stage now that the platforms we're working with are quite mature and stable. And when you're negotiating with someone like us, you can set certain demands in terms of qualifications, availability of resources. You can ask for them to be green if you want, and you can, instead of focusing a great deal of your energies on operations, you can focus on the actual science. So there's a pink elephant in the room. A lot of arguments against doing this. A lot of people want to keep their equipment in-house. They want to be able to touch their servers, like Matti said, I believe. And they think it's cheaper for them to do it here, have it in-house. It can't be secure somewhere else where I can't see it, I can't touch it. And this cloud thing, it's just a thing that will pass, for sure. And of course, we're so special. I mean, we're doing something nobody else is doing. So we have to do this here. It's so experimental and it's completely unique. Well, for the most part, I don't think that's true. I think that's true in a very limited number of cases. I think in those cases there might be some justifications, but I think for the most part, academia is able to use general services, and I think it's very important for academia to mix and match, use best of breed, be a smart consumer. And what I also find is, and we discussed this earlier, is there is a serious lack of metrics. We are unable to compare apples to apples. I will even get, for instance, requests from some university asking for, we want 6,000 cores, how much does it cost? What the hell am I going to say? I don't know what they're asking for. They don't know what they're asking for. So we have to come up with some meaningful metrics to be able to compare these things. And in academia also, we find that there is very little clarity on cost. And we saw this earlier from what you were presenting. Especially in, say, smaller institutions, you might have someone running a room like this full of derelict equipment, inefficient. They might never see the energy bill. They might even not be faced with a bill for the room they're in. So how are we going to, we have to lift this up and get some visibility on what the actual costs are. And that enables us to compare apples to apples, and people that have done that, of course, for their limited use cases, for instance, the HPC that we're running, have come to the conclusion that it makes more sense for them, for that particular application, to actually outsource. And that might not be right for everybody, but I think if you really look in the mirror and give it an honest look and compare apples to apples, that's probably going to be the verdict. Now, there's a word floating around for this, actually. I'm just gonna, I googled this by accident. It's like a Cosmo quiz, 10 signs you might be a server hugger. My favorite is number 5, actually. But still, this is just a comic sidekick here. I think the important thing is where we put this down is where we are able to operate it efficiently, where we have access to green and stable energy supply. Natural free cooling comes into play because that's another, I mean, in data centers normally, large data centers, roughly half of the electricity use is just for cooling. So if we can be more efficient there, and frankly, I'm not impressed with the PUEs, for instance, that you threw up there. I mean, the PUE of 1.5, I'm looking at PUE of 1.16. So that's the kind of efficiency we actually need. Again, clarity on the operating costs, security, and room to grow. Because what happens if you scale this? And also going forward, I mean, inflation in power prices, for instance, in the UK, in the double digits last year, way over 20%, gives you every 3-4 years a doubling of your energy price. And now academia is being squeezed on that end. So if you can plan for this, and you know that your costs are going to be relatively stable for the next decade, that enables you to use that money to actually do some meaningful science. I think that's very important. So now I'm going to switch hats briefly. Since I'm the chairman of the Icelandic Data Center District Group, I'm obliged to give you the speech about the case for Iceland. Again, the free cooling is there, energy available, low cost compared to what you see here, and again the low power price inflation. The infrastructure, the grid itself is extremely robust and young compared to what you see in the rest of Europe and the States. And stability is there. This is a bit of old data comparing Iceland to other markets for hosting. Here is a new study, the Cushman-Wakefield report, just out this year. This is a company specializing in real estate and risk management for real estate. And they do this study now every year, and they've just added Iceland to the mix. And it's number 4 on that list. after the sort of key markets there, UK, US, and Germany. So I'm not going to dwell on that, but here is why. We hardly get a good summer's day. You can see that from the data. It doesn't get too hot, doesn't get too cold, relatively stable. Free cooling. And we have this goal of delivering 1.5 terawatt hours to data centers within the next 8 years. 1.5 terawatt hours. That's probably going to be enough for, say, somewhere between 30 and 40 data centers, modern data centers, to be realistic, depending on what they need. This is the picture in terms of pleasure.
Thank you.
This is the picture in terms of the. This is the picture in terms of the power price. And here's the connectivity bit. For the most part, this is the sort of sore spot, the weak spot. But historically, these connections are quite redundant, and there's a new connection coming up. So I think the HPC model in Iceland is quite secure. So, why did we get into this business? Again, we bought this data center, which was a fledgling startup company in end of last year, December. And we had identified this as a key area where we wanted to bear down with our expertise in hosting. We were already running several sort of tier 2, does that mean anything to you? Tier 2 data centers. And this is the first tier 3 plus data center in Iceland. So it was a shortcut for us because it would take us about a year to build one. So we bought this one. And with it, we got an existing business. We have Opera software. Some of you might be familiar with the Opera browser on your phone. They have, this is one of their points of presence. There are about 40 million people using that data center every second for the web browsing needs. 40 million. It's actually mind-boggling when you just look at a couple of containers. And that sort of, along with the HPC cluster that's in there churning, using electricity and humming away with blinking lights, sort of shows you the potential of this. Again, there's the PUE, 1.16. That's quite impressive, I believe. And we have room to grow there, so if people want to scale up the cluster, that's easily accommodated. We can actually double the size of the current facility, and we can grow adjacent to it another 20,000 square meter facility. So we have room to grow, and not just in terms of real estate, also in power, which is the important bit. Yeah, some nice photos of the surrounding infrastructure. And I've already touched on these points a little bit, so I'm not going to dwell on them. There's a list there of some of our other customers. And yeah, some of these actually deserve a mention. The services that we're currently running in there are the sort of typical services you will find in a cloud provider, and also just in a typical co-location provider. And we find, of course, these services, they are in demand by different customers, but they really sort of have the same requirements. They want the security, the scalability, and I think that's in academia in terms of the comparison earlier. You might actually need a lot of resources for a limited time, but you don't want to be paying for them the rest of the year. You might need them for 3 weeks. So you can scale up quickly and then scale down again, and don't have to worry about dismantling servers or shipping stuff around. We have been working with a company called HRC3 or HRC Cubed in the UK, which is a joint venture between the Hereford Regional College and a company called Transpitech. And we are working there with some of the non-Russell Group colleges in the UK on some pilots. There are a couple of pilots in there. And we've had several requests also in terms of other HPCs. So I can tell you that just since I came on board and started following this, there's a great deal of interest, and it seems to be growing rapidly in terms of this stuff from academia. Again, the bit about the metrics, I think I can't overstate that, so I would just implore you to get clarity on that, and of course we would be very, very willing to help in any way we can in that work. So I guess I'm not going to dwell on this much longer. If you want to hand this back to you.
Okay, thank you very much. What of course makes this a very interesting experiment is that will we indeed get any wiser as to what could possibly be outsourced and what should or cannot be outsourced, and what are the advantages, I mean, in terms of costs and impact and so on. Really, we don't know about this, and probably we will not know in the near future either, because it's so difficult to compare. But we're trying this, and if our users indeed are happy with this, then it becomes very much more interesting. And one thing, of course, is that in terms of users, it's not a free market. It's not an open market, and it is not a fair market. Because, as was pointed out, many of the costs in academia are not transparent, they're not even known, and the researchers do not get a lump of money and go and buy where they would like to buy. They are bound by different funding schemes, and they get possibly housing and electricity for free and local resources. So there is not a free market where one can compare these things. But the debate is open now, and the experiment is being done. And we're not the first, and we're probably not the last who will try to do this. So let's hear if there's any questions to this phenomenon of possible private hosting. Live.
Thank you. I don't know if I have a question. It's sort of a comment as well, because
observation is fine.
Yeah, I think what you raised is of course extremely important, and it's nice to see. You might know that we in Finland, we are aiming at the PUE value of 115, so you don't really need to be very far north for reaching that. But that's not the point what I wanted to say.
You're actually more north than we are, so.
Yeah, that's true. Yeah. But that was not my point. My point was that I think we need to establish a lot more collaboration in this field. And I don't know if you have been exploring the possibilities, because the Directorate H under the DGC net, as it is now called, there is a H4, the ICT for Sustainable Growth, and they are looking a lot into the green ICT and data center business. Yeah. And one of the things which they have, Pekka might know more about this, but one of the things they have been looking at are the sort of criteria to look at. I mean, what are the aspects you should go for to save energy, and because this is still a diffuse field, really. I mean, we are sometimes talking about the energy price or some other things, but we are lacking the metrics in a way of operating. So my point, it was perhaps a long comment, but I think we need to collaborate more, and there are some opportunities from the Commission side to do this as well, which I think we could applaud.
Yeah, I think I would just observe on your observation that from our side we are extremely willing to participate in trying to get that done, getting the metrics done, because that's very important for us, and it's important for the consumers. It's important for everybody. In terms of the energy itself, I think when you come from a small place like I do, like most of us here do probably, something like 1.5 terawatt-hours of electricity sounds like a lot, but it's not. And it just makes a small dent in the universe of what's actually needed So having that amount available and ready for this kind of work is actually important. It means that we have to make use of that opportunity and use that for this, because otherwise it's going to be used for something else, say like an aluminum smelter or something less environmentally important and friendly. So I also think another observation is what I find in markets that are conscious about this is that people find it borderline ridiculous that green energy can be cheaper than non-green energy. That's a sentiment. I mean, I don't know what you feel personally, but when we ask people, say in Sweden or here, this energy is green and you have to pay less for it. They think it's too good to be true. Because green methods of manufacturing electricity, for instance windmills, etc., they tend to be not as efficient in terms of the economy as, say, a large hydroelectric or geothermal plants. But that's, I'm rambling on the energy, I'm sorry.
Right, okay, but I think also we shouldn't forget that, that from the point of view of the researcher, it has to be useful and it has to fix the problem. And that means that, in my experience, in my previous 5 years of work, it has been that some computing is just bulk computing. It needs to be efficient, easy, no nonsense, and just work. Other is very much more instrumental, extremely complicated, and needs to be tweaked. In either case, it seems that it's not just the costs, it's the usefulness, it's in terms of control, what some call having the root password, complete control of this installation. This is also something we need to find out about. Can we indeed have a computer so remote and then have full control over it and offer this to the researchers, even if the researcher could get his energy money locally and invest it abroad? This, of course, also is a question, and that the politics involved in all this.
I think from where I'm sitting, I think most of the hardware platforms are getting more and more generic. It's up to the software layer now in terms of having that access. You don't actually have to be able to go and clap the server. You just have to have that root password to be able to configure. If you need something done to the actual hardware, there are people that can do that for you. So that sort of answers that.
Right. Benny first, and please.
Unless you're building something like a cluster of PS3s or something, which is a different story perhaps.
Well, it's very nice that the cost of power is going down, but if you look at the cost of getting to Iceland on a bit basis, you will have to factor that in, because I have negotiations with your telecommunication provider up there, and then they live in a different time age than the rest of the planet.
I agree with you completely. Here's the deal.
Let me give you an example.
Sure.
My cost for going to Iceland on a 10 gig is 12 times higher than going to New York. That needs to be fixed before it gets really feasible getting there. Otherwise, the network will not have the sufficient money to cope with that. So there's a window of opportunity for Iceland, but they need to get up to 2012.
I couldn't agree more, and this is, I've spent countless hours actually talking to those people, but I think your pricing is a little off. I think it's old. They're coming around.
Well, let me put it like that. I had a meeting recently with the new CEO of Danax.
Omar, yeah.
Yeah, and he says that he actually wanted to see if we could get a higher price for our next renegotiation.
Who are you from?
Nordinet.
Nordinet, okay. I know he's actually squeezing, he's probably putting Nordinet in the same branch as he is with the local telcos, which is probably not the right place for Nordinet to begin with. What's happening is sort of the market is being segmented between the local telcos and the data center industry. And actually, if you look at what someone like Opera, which is capable, or the data centers, which are buying several wavelengths in the fiber, that price has come down significantly just in recent months. And the way I see it is comparing it side by side. You have like two on a graph. It's going to be like these two sort of poles, like this. On the Icelandic one, you have about this bit, which is electricity, and the rest is communications. On the other side, it's vice versa. Now, one of the trends is the electricity price is exploding, and the connectivity bit is shrinking.
Well, it does that for the rest of the planet, but that's not what we hear from your Icelandic friends.
No, I'm telling you, it's coming down. And at the same time, your energy price is exploding. So, where does that leave you in the end?
But anyway, René, you should be glad that they tell you the price before you're locked into their service. But I think computing, there's no one-size-fits-all solution.
No.
And especially for the smaller countries, and most of the countries are smaller countries, I think they have to look in a very wide circle for their computing needs, especially for the dedicated needs. So there's a commodity market, and there we will compete on price, and then of course we will have to add the cost of the computing and the getting there, as René points out correctly.
Yeah.
That's your competition. And then for the supercomputing, I think you have to look very carefully to the architecture of the machines and go to the best machine that fits your problem. And that means that the networking and the integration of networking and computing is what we have to solve for the users, and then the market will solve the rest, I think.
Yeah, I think you're right. I think it boils down to you guys having to be smart consumers. You have to know what you want, and you have to have the metrics to be able to compare what you're being offered. That's the only way you can do this.
Right. Any more needs for interventions in this?
I'm going to stick around here, so if you want to talk after, I'm going to be here. So.
Okay, thank you very much. Introducing our next speaker, it's a use case. It's Håkan Oller. He represents what I would say one of Denmark's high-end users of supercomputing. My customer, so to say, through the last, at least, well, before my time even also. Åke is also a Danish user of Praise, and is invited here to give a kind of user perspective on supercomputing in the high end. Welcome, Åke.
Thank you. So the occurrence of Praise has changed the conditions for the supercomputer much to the better, but it also sets requirements on what to do at the next level down and locally in a national context. And that's what I want to discuss. We need to adjust to this new environment to use it with maximum efficiency. So here's an overview. I'll talk a little bit about our previous experiences and show you some nice examples of what can be done. And then I'll discuss what the infrastructure requirements are from this perspective. So I'm showing you these things also to give you a perspective on these three things that I want to emphasize. The AAA analysis, which is part of the scientific project itself, archival, which is necessary. We have to get rid of the data, but still have access to it occasionally. And finally, we need to be able to give access to our peers, our colleagues, to do spin-off projects, to continue research, to criticize what we've done, and so on, to investigate. So these are the three main requirements. So my own user profile, I've had 40 years of HPC experience. My first experience was when my thesis advisor took me to Maryland, where I could get access to a wonderful big machine, and I was able to calculate 1 million spectral lines of the solar spectrum and show that an approximation that we were using, which was 100 times faster, actually made sense. There was a very small difference between that and the exact case that I was able to steal computing time, essentially. And that's one thing I would like to mention. I don't know if anybody is here who has influence on Praise, but the concept of just retour is a crucial one, and it would be, I would say, my citation record, if that's a measure of scientific productivity, would be enormously much smaller if I would have had to make my country or university or any other organization pay for what I've been using. I've been stealing time in Reading and at NASA Ames without being an American, and around Europe in different machines. And all the time, this principle that Praise has now, where scientific peer review is the only criterion, really should be maintained. one should avoid this bickering between countries about who pays what. So another part of my experience, which is very important, is the Danish Center of Scientific Computing, which was a new initiative and a very, very successful one, because it gave access to renewable resources. There is a 3-year write-off time, which is exactly correct. After 3 years, you really are using out-of-date equipment. And it gave access which is on the same level as price. We have had one of the largest price allocations in the second call. And nevertheless, that is not larger than what we have access to locally on our DCSC finance system. The only difference is that we can burn the allocation on price in 10 days. If they allowed us to it, we could use it in 10 days. And we could make a much larger experiment because they have the larger system and more RAM, etc. But over a year's time, we have similar resources locally in Copenhagen. So there we currently have an Intel cluster which is getting out of date, a GPU cluster with 200 GPUs, and a very important virtual shared memory system, which is our analysis server with lots of RAM, and it should have had high I/O bandwidth. It just hasn't happened yet. So here's a little tableau of examples. We do solar modeling. So in the sun, you know, we have sunspots, and those magnetic fields and sunspots determine a lot what happens in the atmosphere. And what happens there sometimes impacts us on the Earth. And we are currently members of a network that do space weather, not space weather forecasting, but we produce methods for space weather forecasting. So sometimes there are these energetic eruptions, and if the Earth happens to be in the wrong spot, that can have large impacts on telecommunication and power lines and so on. It's rare, but when it happens, it's expensive. So again, just to give you some nice examples, here's a picture in velocity of the sun. It's bright on one side and dark on the other because the sun is rotating. It's rotating in about once every 27 days. But in addition to that pattern, you can see a smaller scale pattern. So if I subtract the rotation pattern and I look at a patch, that's what it looks like. It's sort of just a mess. And if I take now 4 different patches, well, they look very similar, right? But in fact, the scale differs by a factor of 2 between all of these 4 here. And you have no chance to tell the difference. What I've done is I've taken an image and I've filtered it so that it has about 20 degrees of freedom on each direction with a Gaussian filter. And that makes it impossible to tell the difference in size. If I allow you to see the original, you can see that these are the initial patterns. And they differ indeed with a factor of 2. Megameters is millions of meters, in other words, thousands of kilometers. So the upper left one has a size comparable to the half solar radius. So that's an interesting property of the sun, that it has an almost scale-free spectrum. And indeed, numerical simulations have the same property, so one can make a velocity spectrum of the sun by combining observations and models in this fashion here. I won't go into details. And here is a tableau of magnetic properties of the sun. The sun is usually split into active regions and so-called quiet sun, but even a quiet sun has lots of small-scale magnetic fields, which are an excellent example of turbulence. In this case, hydrodynamic turbulence. And the sun is so valuable for us astrophysicists because it's the only place in the universe where you can see things change with time, essentially. I mean, there are a few exceptions where things you can see are not moving in a jet over the years. But that's not really the same as being able to resolve with millions of pixels the surface of the sun and see with high cadence, just seconds between images, something happening, evolving, and you can compare it with numerical modeling. So here's one example where so-called Plage region is compared with The first one was an observation. This is a 2016 squared by 500 simulation, which exceeds the observed one in resolution, but has very similar properties if one filters it with a fuzzy filter. Here's another simulation of sunspot emergence on the sun. It's the first time this has been possible to do. It was done by a colleague of mine using our code about a year ago, and this is a breakthrough. Here's a zoom in on the central part. And for you, it's just a nice pattern, but for us, it's a fantastic example of hydrodynamics controlled by magnetic fields in the sun. So the next point I want to make is the importance of visualization and the impact of visualization on the e-infrastructure needs. Visualization in 3D, and particularly with time available, is so important when one wants to understand what's going on qualitatively and semi-quantitatively. One can then, of course, also make quantitative and statistical analysis, but in order to have a basic understanding of the physics, 3D visualization is very important. That's, of course, a problem, because the higher the resolution, if you have, for example, a 2,000 cubed data set, the point of having 2,000 in resolution is that on the finest scale, which is a few mesh points, things evolve. And they evolve on the time scale of a few time steps. So in order to really make a time-dependent 3D visualization, you would have to save a full snapshot, which is 1/10 of a terabyte perhaps, every 10 time steps. And you have maybe 100,000 time steps, you can figure out how many petabytes of data that is. So sometimes this is not possible, and sometimes you have to make compromises. So a major requirement there is high bandwidth from the data storage to the computer that visualizes, okay? And then from the visualization, which may be going on, for example, in Yiddish or in Palo Alto, and I'm sitting on my laptop somewhere, even on the train or at home, and between those 2 points, one can use wavelet compression to reduce the bandwidth requirement, and one can always zoom in to a certain point. So there are these 2 different bandwidth requirements, and the data I/O bandwidth is a really important one, where we haven't done too well recently. If one looks at the major data centers, and the access time of data sets there is fantastically much shorter than what we can offer locally. So here are some other visualizations with a tool called Vapor from National Center for Atmospheric Research in Colorado. This is a very nice piece of software that does use wavelet compression. And this is a poor man's bandwidth tool. So you can take a snapshot, convert it to a series of files at increasing resolution. And you can ask, for example, for the wavelet compression that compresses things a factor of 100. You get that first. It's reduced with a factor of 100 in volume, but it shows almost the same thing. It's a little bit more fuzzy. But it doesn't correspond to reducing the resolution with a factor of 100, not at all. It just has a little bit problem to catch edges and so on. It's like a JPEG compression of an image. And then when you're not satisfied with that, you get the next level, which is maybe a factor of 30 compression or a factor of 10 compression. Factor of 10 compression is almost indistinguishable from the actual data. And you can do quantitative statistical analysis on a wavelet compressed data set with a factor of 10 compression. So here's a number of nice examples of that. And then I finally want to show you the record-breaking simulation that we did with the first PRAISE grant that just finished the 1st of May. So we had a successful PRAISE grant in the second call, and in the fourth call we had 2 grants. So we're now running on 2 different systems. This has been produced at Eugene in Jülich, and that's where we do the solar work, and we do star formation work at some other center. So this is an image of the sun with magnetic fields marked in dark and light for positive and negative, and we're zooming in on a particular area. We're taking that magnetic field from observations. We use that at the bottom of a model, and we use also as a boundary condition the motions that have been going on in that little patch. They can be simplified into a boundary motion model. And then we extrapolate the magnetic field first in a potential form from that pattern, and we then evolve it using first a so-called fluid model, a magnetic hydrodynamic model. That is a standard thing that has been done for many years. We then zoom in on a particularly interesting area, and we make a particle simulation, which is something very new. Particle simulations are more expensive, but they can catch non-thermal behavior, in particular particle acceleration, which is what we are interested in here. And so here's a particular magnetic topology that gives rise to particle acceleration. And we model this with 135 billion particles. This is not quite as many particles as the cosmologists are using, but their particles are much more stupid. They only move and give rise to gravity. Ours are charged and they do more complicated things. So within solar physics, this is a record-breaking simulation with also a large number of cells. We have about 30 particles per cell, and it's a thing called particle-in-cell technology. So in that particular model, we discover that there is particle acceleration going on in a particular location, and we can study that. We can look at why particles are accelerated, particularly at that point. So let me discuss specifics related to praise. One very important constraint is, of course, that if we hadn't been lucky, we'd had for 1 year and then nothing. So it's a huge resource, and suddenly it can be taken away. And you end up with tens of terabytes of data that you have to remove within 2 months, or move rather than remove. Until now, all access has been 1-year projects. From the fifth call, they have so-called multi-year access, but that's 2-year maximum, so multi is a bit of a misnomer here. So for a healthy research national environment, this must be complemented by local resources for development, for teaching, for tutoring, and so on. And training of new users is absolutely essential. At the moment, we've had a few bachelor students doing projects, and it's the same every time. They come with great enthusiasm, and then they learn the hard realities. The stupid program doesn't work, and it crashes, and it's difficult to get the parameters right and to analyze. And we have to be very positive on the one hand. We have to be good tutors, but we also have to have good resources. Otherwise, they go off to some other subject and abandon this very difficult thing called HPC. So, to get back to these 3 things, analysis, archival, and access. Analysis requires that you have huge RAM size. For example, a 2,000 cube snapshot is 8 billion words, which is 32 billion bytes. And each snapshot has 8 variables, so that's 240 gigabytes of data for a single snapshot, which you'd better have in memory, otherwise things get very slow, because it takes a long time to read in such a thing into memory, at least locally it does. You also want to have multi-core, so that computing, for example, statistical averages can be done with reasonable speeds. And many of the current tools, for example, MATLAB and interactive data language and Mathematica, support multi-core use. And you want to have high input-output bandwidth. So a virtual shared memory system like the one offered by ScaleMP is ideal in this respect. And at the local DCSC facility in Copenhagen, we have a system which is similar to the one called Gordon in San Diego. Gordon is much, much larger. And the name Gordon has been chosen because in a few years they will change to flash memory, and then it's Flash Gordon. So far in Copenhagen we have 4 nodes with 48 cores, 256 gigabytes of RAM, and 200 terabyte disk, and it's expandable. Whenever somebody can afford it, we can add a node, and the nodes don't have to be uniform. If in a couple of years a node is not really good for computing, it can be used only for its disk access or its memory access. So it's a really expandable and future secure system. Archival requirements. As I mentioned, data needs to be moved over PRACE systems 2 months after a project ends. And even if you have a new project, of course, that project generates its own data, and you can't just use the storage capacity of the new project to store the old data. So you need to have a simulation pipeline, and the pipeline must have an open end at the, where you can get rid of data without really losing it. So you do runs, and if you do it on a system in Stuttgart or in Jülich or in NASA Ames, there is a hierarchical storage management system where you simply put the data there and it's rolled off to the types. And, but you still have access to the file stubs, which is very important for having an overview and organization of your stuff. And if you clean up, if you remove some files, they're just marked as non-existing on the archival system, and they don't have to be loaded in to be deleted. Fortunately, both NASA Ames and Jülich have recognized the need for analysis. So when we first got the grant at Jülich, there was nothing. There was no front end that had memory enough to do analysis. And the possibility was to get an account on a system called UVIS, which is a visualization server. But each node there has only 24 gigabytes, so that's not really sufficient either. But after a few months, they installed a couple of large front-end machines that have access to the GPFS, the work system, and the archival system. So they have a really good setup there. NASA Ames has a very similar setup with an archival system. And we are hoping to get one at DCSC KU. We have money allocated for it, so we just need to get it done. This is so important because otherwise you simply have to delete data sets at the end of a project in order to have room for another one. You can of course keep buying larger and larger disks, but having an archival system greatly expands the maneuverability of your projects. You can't really cope with it by just expanding the disk volume. So in addition to being able to continue projects, to make spin-off projects, this can also easily handle the third thing I mentioned, namely peer access, to give access to your colleagues, to your competitors, and to people who would like to start from your data set and do something different than was intended from the beginning. So a system that gives access in that way should be flexible. Until now, the only way to give access to people was to collaborate, so that they were counted as collaborators, and therefore they could get an account in the local university system and so on. But why should that be necessary? Why should you not be able to say, this guy from San Diego wants to access my data, and he doesn't want to copy 10 terabytes, he wants to analyze it locally to get something sensible out of it. Why shouldn't we be able to give him access for a month with no big apparatus? And as I mentioned, archival hierarchical storage management is really the preferred method. Peer access, which I just discussed, is really easy to combine with existing analysis facilities. And the importance is the one that I mentioned, that a collaborator or a peer or somebody who wants to have access usually doesn't need the whole data set. They need to have a slice or some kind of projection, and they know best themselves how to make it. If they have to tell you to do it, you don't have the time. Maybe you're not interested in spending the time just so that they should have a paper. Well, you can be a co-author, but there are so many projects you're involved with anyway. So the best is to give them access, let them muck with the data themselves for a certain amount of time, and then that's saving a lot of bandwidth and a lot of human time. And it should be easy to combine with existing facilities. But to summarize, what's specific about praise access compared to when we had our own machines only is that it's intermittent access. You need to cope with the fact that perhaps you only get 1 year. And in any case, if you get 2 years, it's a new project, and you need to have an established pipeline for the data. Of course, it would be nice if praise established something as a European facility, but that doesn't seem to be in the plans. One also needs to complement the resource itself, because you need to be lucky, or you need to write a good proposal to get a level 1 grant. And in the meantime, you need to have slightly less capacity available, either through a local computing system or through a local level 1 system. And why not one on Iceland? I'd be happy about that. I'd never have to travel there. I have never been to NASA Ames. I've computed a lot there. I've never been to Yiddish. Why should I go there? There's an internet, so whether it's in Iceland or Stockholm or Helsinki, I really don't care. The other component of praise problems is that you have to get rid of the data after a short time. So the praise-related requirements locally are essentially data facilities. But data facilities does not mean just storage. It also means analysis capacity and the possibility of giving access to your peers and competitors. Thanks very much for the opportunity to discuss this with you.
Okay, thank you very much. One of the interesting questions here about praise is, of course, this, as you said, with the just retour. I mean, the fact that actually we need to pay for this. And as it is now, it is basically almost a free ride for the small countries. It's just some one fee we pay, but this is going to change, so we will have to pay. Having to pay as a national infrastructure provider, we need to know value for money. We take your word for it, it's great, but you, of course, don't pay for it. If we are supposed as a national infrastructure to pay for it, we should of course think the alternative cost. If we would maybe put the money in North Finland or in Sweden, or just give you the cash, or build something in Denmark, how can we know what we get best value for money from the point of view of the Danish taxpayer? This is very difficult.
The best value for the money is to not use the principle of just retour, but to let scientific peer review determine who gets access to the largest machines in the world.
But it has to be paid for.
Yes, exactly. And the current system does that. Somebody is paying for the installations at Yiddish, and they have decided to make it available to praise. If they decide to change to just retour, fine. I mean, that's their decision, but it's not a good decision. It's not an optimal decision. It's one that will reduce the scientific output of the system, because the maximum output is when you only decide on the basis of scientific merit. And I'm not so sure that this is already a decided issue. I'm a member of the Praise user group, and it was just 2 months ago that the Praise chairman was very proud of announcing that not only is there a free access to calls in Europe, but from the 5th call, anybody in the world can access and propose to use the Praise resources. Likewise, we can send proposals to the American initiative called Insight. There's a deadline in a few weeks, actually. And anybody can make proposals. If you want to propose, for example, to Seneca in Italy, you have to have an Italian PI in the project, but you probably have some colleague in Italy. So this is the way to maximize scientific productivity. And if you want to question the value of science, but that's another topic altogether. Within the presumption that we want to do science, the most efficient way of doing it is to have peer review and nothing else.
Okay, thank you. I just know as I'm sitting in the Praise Council,
yeah, you're in a hot chair,
and I know a lot of other council members here today, and this thing about paying for the machine is something that will not go away. Yeah.
No.
Okay. Any Goodman?
Yes. Thanks for a very, very interesting presentation. So to continue that line of logic that you gave for giving lots of resources to merit-based science, like the best science in Europe or in the world, but it still seemed that you had some problems with transmitting the data afterwards, storing it, making it accessible. So maybe it sounds to me that the computing resources is not sufficient. That you would need a sort of a complete package of services.
Yeah, well, the national level needs to adjust to the fact that we have Praise, and to give an example of the frontline things happening in Praise. If you look at the decisions of the 4th call that were made available a few weeks ago or a month ago, there's a huge allocation, essentially a whole machine for a year, maybe 10 times larger than the typical Praise grant, given to break or to finally solve a problem that has been a riddle in astrophysics for 30 years, or for, I mean, it's been attempted to supercompute this problem for 30 years. And the problem is, how do you make supernova? A supernova is a completely common phenomenon, and in principle, you think you understand it, but people have failed again and again and again to make working models. It seems that you need 3 dimensions. You need to have neutrino transport and all kinds of expensive things. And Praise has recognized that. They've given one person a huge grant to try to finally break this problem. He happens to be a German, but that's a coincidence. He didn't get it because he's German. He got it because he's the top player in the field, without doubt.
Okay, well, anyway, we can be sure that we can hardly ask the Germans to pay for our supercomputing, so we will be billed for this.
Of course we can ask them to pay for it.
Right.
Whether they will do it is another thing.
I would like to ask you some physics-specific questions and then some computing-specific. What kind of simulation is this? Is this like solving Navier-Stokes hydrodynamic equations? And if so, how many equations are there solved simultaneously? And then, congruent to that, you said you have 135 billion particles. Does this mean that you store and you have the coordinates and the velocities of 10 to the 11 particles simultaneously at the same time that you can control?
Yes.
In addition, let me ask all together, then you can answer them at the end. It's nice to see all these figures, which you will explain how they come about, but do we have, I know that we do, but do you have experimental data to compare these? It's nice to have good models, but a model by itself, on its own, eventually doesn't compare to real world. We know that it's not so much use. So has it been possible to actually do this kind of comparison to verify what you're doing. And now on the computing side, you said that several of these were done on systems like with 80 cores and 256 gigs, which are very abundant today. They are not very.
No, this was the analysis.
This was only the analysis, not the simulation.
No.
Okay. My point was, what integral part of it was it necessary to be run on Praise, and adjunct to that, if it would be done on a large grid system, where you have a huge number of, tens of thousands of cores that are distributed. I'm sure you know about this, and if in that case might be cheaper to do because the grid parts belong to the different laboratories in different countries.
Very fast. It would not be possible on a grid system. This used 2 to the 18 cores, 262,144 cores on essentially the whole system at Jülich. So it needs that, and it needs a very high bandwidth in order to do it. What we do is that we solve the Maxwell equations for the electric and magnetic field, and we use the particles to compute the two things you need, the charge density and the electric current, to complement the Maxwell equations. So these are ab initio particle simulations, and as I mentioned, the target is to explain particle acceleration. And as I also mentioned, the sun is an excellent comparison because we have very, very detailed observations of the sun. We know that there is a power law dependence of accelerated electrons that ranges up to a couple of hundred keV with a certain slope, and then it changes to a much steeper one, but it goes up to GeV. And we were now able to explain for the first time ever the first part of the spectrum. We know why that is there. And it was only possible because we were extremely lucky. We made some incorrect decisions of parameters that turned out to be exactly the correct ones in the end. If we had done what we originally planned, I think we would have failed. But we succeeded, and we could only succeed with the largest possible run, which was a 36-hour straight use of the entire Jülich system. And they have a max runtime of 24 hours, but we discovered after about half the time that we wouldn't be able to finish, and we had no chance to dump the thing. So we called them and said, can we continue? And they said, yes. So we ran 1.5 months of grant time in 36 hours and made this experiment. And the smaller ones that were the next level ones would not have proven the same thing.
Okay, thank you very much, Joachim. Okay, let me introduce our next speaker, Christopher Navaki. It's also a use case. It is this time bioinformatics. It's also one of, how should I say, representing one of my biggest customers in Denmark, grant holder. We will hear from Christopher, I think, as a user of the infrastructure, and also you have a lot of European activities, as I understand, and a lot of activities that not necessarily are in Denmark, international. Yes. So the word's yours.
Thank you. Does this work? Yes. So, firstly, I would like to thank the organizers for the invitation. And secondly, I just wish to assure you that I'm completely aware of the fact that I am the only obstacle remaining between you and the pleasures of the evening. So I will try to be brief and to the point. But how do we do it? Do I still have my half hour, or shall I try to cut, or what do we do?
We have to catch this boat, you see.
When is the boat?
And it's just around the corner. It's in 45 minutes.
Oh,
so
yes, but
transport here. I'm not something.
But it is walking distance from here.
I think you can at least do 20 minutes without any concern.
20 minutes.
Yeah.
So
5.
Okay, so you help me with calling me back to order if needed. Yes. Okay, so I should start perhaps by introducing myself. I work for a bioinformatics lab here outside of Copenhagen, the DTU, Technical University of Denmark. It's called Center for Biological Sequence Analysis. It was started roughly 20 years ago and pioneered bioinformatics in this country. It currently employs roughly 100 people, 100 scientists that is, and my function there is the head of system administration. So I will be giving a user case here, although I'm not a bioinformatician myself, but my daily job is to serve bioinformaticians and biologists and facilitate and help them to do their work. So after this, let me just go to works, to the subject. And the subject is, in fact, biology, because bioinformatics is just a part of it, and whatever happens in bioinformatics is very much determined by the developments in biology, and those are very dramatic these days. Biology is in a state of paradigm shift, you could say, or revolution. Many words have been used to describe it. It's a fantastic process and very dramatic. So I have built this presentation around three main points. One is this dramatic paradigm shift. The other is the need for new infrastructure that this revolution causes. And the third and last is a brief report of an ongoing initiative already that addresses the issue and tries to solve it. So what is this paradigm shift? That is, we could see it in a way as a change of scope. When I started in this field 20 years ago, the biologists would think of genes, analyze gene by gene, perhaps groups of genes and proteins that those genes coded for and their function. Then it moved over the years to gene collections, all genes for a given organism. For example, Homo sapiens has 25,000, only to proceed further into the entire genome, because it turned out that what we, or the scientists erroneously called junk DNA, that is the DNA that is not genes, was not junk at all. It contains hundreds of thousands of functional places that do things that we didn't know about, but now we are learning. And then finally, this moves into studying genomes of entire populations. First, it was just 3 extra people, then 5, then 1,000. Now we are talking of entire peoples. So you could ask yourself, what brought this about? What made it possible? Why did it happen? And then the answer is, not surprising, money. Simply money, and specifically the reduction of the cost of sequencing, cost of simply sequencing the DNA. And this happened, as you can see, rather dramatically. For many years, the cost of sequencing followed Moore's law, more or less, and then suddenly something happened. And that was the technological breakthrough that happened and made it possible to start sequencing like crazy. That happened roughly 2008, 9, and completely refurnished, remodeled, rebuilt the field, opened new possibilities, and created new stress and challenges that had not been there before. So people started sequencing. Here you have a number of examples of projects that started there. Some of them are ongoing still. And that immediately produced an imbalance in the situation, in the entire science, because the amounts of biological data started growing faster than other key indicators in the field. So specifically, CPU power, speed, could not hold up, and the disk capacity and the connectivity, all that grows, of course, but it does not grow by far as fast as simply the amounts of biological data that we have. Here shown by simply the number of racks in the EBI machine room, which is an European Institute for Bioinformatics, that is a union-owned initiative. And their data size, the sizes of data they hold represents very, very well this explosion. So what we are looking at here is a so-called disruptive technology. This word has been used, or this term has been used much, but perhaps nowhere with greater justice than here. And René has warned me that I would be talking to non-bio people, so I've been thinking of trying to come up with some metaphors that would bring this dramatic situation sort of more to your imagination. So I've been thinking of three. The first one was simply riding a horse that you don't control, that you are not controlling. So that is the feeling, I think, that many biologists and people in this business have. That simply this is going so fast and so suddenly, and things are simply impossible to control. The other analogy or metaphor would be what happened to physics in the 20s. And that is something that has moved already into the field of legends, so everybody knows about quantum mechanics and relativity, and it all exploded, perhaps. Some people might correct me here, after the First World War. The physics was suddenly completely different, and that was a paradigm shift, or several. And the final analogy I have come up with is one that you perhaps might dislike, but I think that the invention of the machine gun in the end of the 19th century is also something of the kind. Similar. We have an improved performance performance that is improved at a rate at which users cannot adapt. They simply cannot adapt, and that's what happened with the machine gun, with, of course, horrible consequences, as you know. So this causes for new infrastructure of the kind that biology has never needed, never used, never even imagined. So I continue hammering this point a little more. That is, it turns out, as my colleagues tell me, or my scientists tell me, that this next generation sequencing, this explosion of genetic material that is sequenced, is not the only sort of explosive or disruptive thing that is happening. We have also this mass spectrometry, also may be disruptive, and imaging and analysis of images. There will be more images and they will need to be analyzed. So that is, this seems that it is not just one phenomenon, it's just a start, only a start of what's happening. Further, there is also, there are many aspects to it. This is not only a revolution that calls for new IT infrastructure. There's also a question of organizational infrastructure, training of people, and generally working smarter, because the generation of data and potential insight outperforms the development of hardware. And as if this was not enough, what needs to be added here is that this data has enormous diversity, because downstream from this DNA that is coming out here is all sorts of related data. There is a question of expression of different proteins in the cells, and there is a question of those proteins performing different functions, aggregating, and then in the impact of those discoveries those discoveries might have on healthcare, production of drugs, drug discovery, etc. All that needs to be integrated. So this is just to indicate that we start with genome and genomic material, and then we proceed to proteins, cells, and organisms, and all sorts of things that are simply inspiring and frustrating in one. So I, at this point, I think that we can consider this point made, that biology is a sort of wonderful crisis. So what I proceed to is to tell you a little about a project that is ongoing already, whose aim is to do something about it. And that project is called Elixir. It's one of the 35 initial S3 projects. And its purpose is exactly to prepare and solve, well, to a certain extent at least, this sort of crisis-like situation. So I accelerate here a little. The main point is to prepare infrastructure that would allow management, integration, and usage of these enormous amounts of data that are being produced. And this is really needed because currently we have a disproportion in expenditure. As you see here, the here we have the spending on that is done on production of this data, and that succeeded beyond the scope of our prayers. But at the same time, you have rather meager, almost laughable cost used for preparing the infrastructure and analysis of all this. So that's what this Elixir project is supposed to do, to sort of address. One thing that needs to be added here is also that this is a sort of youngish science, and rather dynamic and rather new. So the apparatus of tools and softwares is very diverse, but also very immature in the sense that it is fragmented and not very well structured. So what you typically see as a bioinformatician or biologist is a mishmash of tools, and they don't speak to one another, and they all use different formats, and the formats are not settled, and the new data types come in, and they are not settled either. So this is also a part of the infrastructure, that is a sort of soft infrastructure that this project needs to do. The purpose here, or the bait that we have invented, is that the data, be it the new produced data or stored data retrieved from databases or output of tools, should be passed on arrival, so that he who uses it or she should find it convenient and easy to process it further and refine the analysis. One more step, or several. This project has several work packages, and they go after these relevant issues, tools I mentioned a moment ago. But there is also a question of as I said, it is not only about the IT infrastructure, it's also about human. I think I should say that one more thing is that Elixir is connected very much to other S3 projects in the bio domain, and intended to assist them with infrastructural needs as well. I think I skipped this. Now the organization of Elixir is worth mentioning, because it's being thought about as a highly distributed effort. There is a central hub, that is European Bioinformatics Institute, NMEBL. These are unional initiatives, and they are going to coordinate this. But there will be plenty of side hubs around it. Some of them will be national centers for different countries. Some of them will be hubs of Elixir without being national centers. So the structure is very, you could say, elastic. And that has been necessary, I understand, for not least political reasons. And financial, because it is not only from Brussels that financing comes, it also comes from national governments. Denmark has a grant, for example. So does Sweden, Holland, and many others. And this is important because we have recently seen demise of a similar American initiative that we already heard about when Elixir was in a preparatory phase a couple of years ago. That was an example of that. We had some experts that we invited to a committee to evaluate what was going on in the other parts of the world outside of Europe. And they gave this KABIC as an example of how not to do it. It was highly centralized, highly normative, and it never flew. So it has recently been put in the grave. So Elixir is trying very, very consciously and consistently to avoid this kind of mistake. It should not be top-down. Well, now to the final part. I just bring this paradigm shift once again here to make additional point here. It is that as we are moving from genes to millions of people, we are also moving and invading the privacy of those people, so that this data is threatening to become very person sensitive. We are starting sequencing people in big style, and that raises ethical concerns that further complicate the infrastructure to be, because it has to have a significant and stringent security component. So questions like conflict between federation and centralization, is important, and it's being debated very much. So I'm going to, well, I say this again because the time. And here we just go to one sort of homegrown example that illustrates this. In the lab employing me, we have a number of projects in which there is one sensitive part that has to be, by the demands of those who run the project, has to be enclosed in a yet another firewall on top of or inside our main firewall, and the control to it is strictly, the access to it is strictly controlled. This is usually the fact caused by partly ethical concerns, partly commercial, because if you want big pharma to participate, they will put very stringent demands on access and secrecy. So we are trying to solve it in different ways. One is that there is this hermetic box containing a project server on which analysis is done. It has encrypted storage. It also pulls resources from our publicly available data warehouse. And then the researchers should be able to log into it directly and do their stuff. This is highly debatable because there are also security concerns, as you know, coming from just using SSH from the outside to such a box. Sometimes we need more compute power than such a little server can provide, and then we bring in a supercomputer temporarily into the box. Then it becomes lost for the rest of the world, but then it does its job there, and then it's moved out again. So we're trying to run both those solutions in parallel to satisfy the needs of projects. So, good. I'm doing good, I think. So, to summarize, this speaks for itself. This is a serious situation, but and biology is a sort of, you could say, a crisis and a promise in one at the same time. And this elixir initiative seems to be the answer, at least the best answer that the community has been able to produce so far. Thank you.
Okay, thank you. So this was our last presentations, but so 2 use cases. So what can we, in terms of strategy, conclude from this? How do we serve our customers? Any questions? Otherwise, I have one to suggest. Okay, here. Certainly.
Stephen Wolf from Internet 2. I was one of those who applauded the demise of CAD, as many people did. I would commend to you, for purposes of comparison with Elixir, a lesser known but long-running project called Pragma. It's been running for about 10 years. It is a highly decentralized, nobody in charge scientific set of scientific expeditions in the biology field. I recommend it to you.
Thank you.
Okay, so if there are no more questions, I would like to ask one. So I've been thinking that much of this infrastructure which we build, and we build for specific communities, is on a general purpose basis. It's also the rationale for the European Grid Initiative, that it's for everybody. But I kind of get the idea from Åke and from you, and coming from the high energy physics background where I had my office, that these 3 as examples cannot really use the same infrastructure. I mean, you have this conglomerate of databases which you need to connect. Åke's needs are somewhat much different, so is there a basis for a general purpose infrastructure, or would you rather say that once you reach a specific size, you really can do it yourself if just given the money?
So I think that the only fair answer to this is sort of both a yes and no at the same time, because it is indeed so that in computing, in biology, or in bioinformatics, we do have specificities, and some of them are severe. They are mostly threefold. One is the dependence on data. Data is ever present. it is diverse and unsettled, and this has been, in fact, the reason that biologists or bioinformaticians have not been using the traditional grid middleware over the past decade or so. The other is the ethical and commercial concerns that some of the data needs to be kept in hermetic boxes of different kind, and that also makes it more difficult to use common solutions. But with this said, I would not like to say, because we have heard this statement, that you think you are special, but you are probably not. So we are not that special that we would have to have a parallel universe of our own, separated from all the you other guys, because this is clearly not the case. Much of our computations can be done on resources that we share with other people. It's obvious that it can be done.
Okay, thank you. Right, Steve, thought I could get a question out of you.
I don't want to disappoint. So I think the issue that we always have with this is what exactly is common? What are the common elements? Okay. So with Elixir, there's the challenge that you have of having, I think, estimated about 600 different data sets across Europe that you'd like to get structured access to in a predictable way. So one of the things that EGI has done is, for its 350 data centers across the world, has put in a structure around monitoring services, support for services in terms of help desk and things like that we've been talking to Ewan about in terms of at EBI, about how can that technology and that expertise be made available and exported to the Elixir community to make use of our common operations infrastructure. Now, quite clearly, the services that you're operating are very different from the services we're operating for many of our own research communities, but the technologies that go around the operational infrastructure are generic and can be adapted to help some of the work that you're trying to do. So I think the question is will Elixir use the same services that EGI uses at the moment? Clearly not, as you've said, there are many differences around what you want to do. But is there work that EGI and other infrastructures can provide to the research infrastructures that are coming along? Then yes, certainly I think there's expertise and knowledge that can be exported to this and other communities.
I could perhaps answer to this in this way, that over the years, as we were looking at the development of different solutions for making resources common, we have discovered that the only way that seemed to make sense for the life sciences community was being very much service-oriented, so that the responsibility how a service is discharged and provided lies with the provider of that service. So I think that this ball should be played in this way, that if whoever provides a service in life sciences, or indeed any other science, should be allowed to sort of manage their show, if they feel that they can use this or that technology, that middleware, that solution or other, they should be allowed to do so. And in some cases they will opt for their own hardware in a very secret cellar or basement in the lab, or in some other cases they will opt for sending this data for analysis elsewhere over a fast line. But I don't think that a general solution or general answer to this question exists. It should be decided at the service provider level.
Okay, so any questions? I think not. In this case, I think that concludes our day. We'll continue tomorrow. We'll hear something about regional collaboration. We'll look more into the more softer sciences, their needs, and we'll also hear a little more about big-time cloud computing and so on. But as for now, we go to the canal and have a look at Copenhagen. It's also a kind of infrastructure, very weather dependent. As for now, it seems as if it's not raining. So we have about 17 minutes to get down on the street. There will be some transport there to wherever this canal trip starts. I'm not quite sure, but down at the in front of the door here in 17 minutes.